It is without doubt, in my opinion, the biggest scientific discovery of my lifetime, and without doubt one of the biggest scientific discoveries of all time. So I'm tremendously excited. It's a real pleasure. It's almost an honour to be a tiny part of this discovery. I mean, we're all part of it. It's like this day will go down as one of the great days in the history of science, I think, and that's not overly hyperbolic. It's that important.
Particle we think was in fact a particle like this was the fuse that set off the explosion which created the universe.
It's the largest scientific instrument ever built, and it's tunnel Europe's largest civil engineering project.
Things come to an end, and this will be the end for the Tevatron. It's had a glorious career, 25 years, which is...
Physicists believe they have finally identified the particle known as the Higgs boson.
We've observed a new particle. We have quite strong evidence.
As a layman, I would now say, I think we have it.
Well, where do we start? The first thing to know about the God particle is don't call it the God particle in front of any scientist you wish to keep on your good side. It's a name that's attracted criticism over the years because it really is a terrible name. It doesn't tell you anything about the particle, not even who discovered it. Unless, of course, I missed the Bible verse where God built himself a particle accelerator to look for it. The story behind the name recalls that Nobel Prize winner Leon Lederman wrote a book which he titled The Goddamn Particle in the 90s, referring to how difficult and costly it was to find the Higgs boson. His publishers weren't happy with that title and went with the much more show-stopping The God Particle. Unfortunately for Lederman and the rest of the physics world, it stuck. Most people know a little bit about the Higgs boson here and there, enough to make you sound smart in a conversation, but not the whole story. So why is this God particle so important? If you ask most scientists this question, they'd probably give you the usual spiel about how the Higgs boson gives mass to everything around it, much like the building of a local McDonald's. But this explanation is actually wrong. The Higgs boson is just a layabout like the rest of us. It doesn't do any of that. It's a fraud. It takes its credit from its much more impactful but sadly unknown father. But to understand who the father is, we need to know a little bit about quantum field theory. Now these are exceptionally complicated theories. They are meant to hurt your head to try and understand them. I've tried to keep it as simple as possible without making it sound like the ramblings of a madman. So here goes. We know the universe is made from fundamental particles. These include electrons, quarks, photons, and so on. But these particles might not be as fundamental as you think. Sure, they aren't made of anything else, but they are produced by something else. These are the quantum fields. Close your eyes and forget about a universe of particles. Instead, imagine that the universe is full of fields, which permeate and exist through all of space-time. Each of these fields is associated with one of the fundamental particles, like the electron. These fields can vibrate and oscillate in specific places like ripples in a pond's surface. What do these vibrations represent? Well, they are the particles. As unintuitive as it sounds, our entire universe is just oscillations in various fields. Like writing on a paper produces letters and words, oscillations in these quantum fields produce particles. Each field produces a unique particle, and these fields and their particles make up everything we know about the standard model of particle physics. If this is confusing to you, don't worry, you have very good company. As Richard Feynman once said in a lecture,
and I think I can safely say that nobody understands quantum mechanics.
Today, quantum field theory and particle physics in general are quite airtight theories and have relatively few problems. But this wasn't always the case. If we wind back the clock to 1960, the landscape of particle physics looked a lot different. And there was a big hole in it. The theory at the time suggested that all bosons should be massless. What are bosons? Well, they're these things here. Electrons, protons, and neutrons make up our world, but bosons are how they interact with each other. They hold quarks together into protons and neutrons, cause radioactive decay, and cause charged things to attract and repel one another. So, was the theory correct? Are all bosons massless? Well, no. While gluons and photons are massless, the W and Z bosons actually do have mass. So what now? Physics is broken? Quite the pickle, but have no fear, there was help at hand. We can now introduce our star cast. You may know it as the Higgs boson, but it had many more founding fathers than the name suggests. Peter Higgs was one of 6 people who released a paper concerning the Higgs field at around the same time. The rest of the cast consists of Robert Brout, Francois Englert, Gerald Guralnick, C.R. Hagen, and Tom Kibble. So why is it only named after Higgs? Who knows? But it sure rolls off the tongue better than the Englert, Brout, Higgs, Guralnick, Hagen, Kibble boson. And yes, this has been put forward as a name. They realised that if you introduced a quantum field with certain properties, then all these mysterious massless bosons could be fixed. So what were these properties? And how did they fix the problem? Short answer, it's very complicated. But if you want to know more about it, and are well versed in scientific literature, I'll leave a couple papers in the description which I wrote on the subject while at university. So in essence, the Higgs field interacts or couples with other fields, and that causes the particles of those fields to have mass. So the Higgs field does all the work. The so-called God particle is a fraud. So what is the point of it then? Why do we need to find the Higgs boson, and why did we spend all that money looking for it? Well, like I said earlier, for every field, there is a particle that comes with it. We can't see the field, but we can see the fundamental particle, which is the Higgs boson. So in order to prove that the Higgs field exists and its mechanism is real, we have to find the Higgs boson. So yeah, that was some tangent, but I hope you got something from all that. Particle physics on the theoretical level is very hard to explain. I mean, look at this equation. And yes, it is a real equation. It's meant to lay out all the possible interactions between the fields and the particles that we know of. So in a way, this is almost the recipe of the universe. It says what particles are in it, how they interact with each other, and what forces are produced. This is probably what Neo saw when he cracked the Matrix. But now for the main event. How did we find this pesky particle? Higgs bosons aren't generally just flying about. They have to be artificially made in extreme conditions. And once we start making them, all we have to do is detect one. Sounds easy, but this task took over 40 years and billions of dollars. The ways of making a Higgs boson are called production modes. There are 4 useful production modes for making them: gluon fusion, Higgs Strahlung, vector boson fusion, and top fusion. Fancy names, but they're all effectively doing the same thing. 2 particles will collide at very high speeds, providing enough energy to form a Higgs boson. This is where particle accelerators like the one at CERN come in. They can make these production modes happen by accelerating particles to incredibly high speeds. Here's a quick rundown of how they work. Gluon fusion. Collide 2 protons together to fuse their gluons together. The collision energy can be enough to make a Higgs boson. Higgs Strahlung. Collide a fermion and an antifermion, like an electron and a positron, and the energy from their collision and annihilation can produce a W or a Z boson. If this boson has enough excess energy, it can emit a Higgs boson. Vector boson fusion. This time, there are 2 fermions, like 2 quarks, which pass nearby each other. If both of them have enough energy, they can emit a W or Z boson each. These 2 bosons can then fuse to create a Higgs boson. Top fusion. 2 protons collide with each other, fusing their gluons together. Each gluon fragments into a top quark and an anti-top quark, leaving us with 2 top quarks and 2 anti-top quarks. A top quark from one of the pairs and an anti-top quark from the other pair then annihilate with each other, forming a Higgs boson. Okay, so we know how to create a Higgs boson. Basically just smash a load of particles together and see what happens. But how do we detect our god particle? Because the Higgs is such a massive particle at around 130 times the mass of the proton, it is very unstable. The king of vanishing acts, the Higgs only sticks around for 1.6 times 10 to the minus 22 seconds. Understandably, this makes it very hard to find. But it's these very decays that is the key to opening the door on the Higgs boson and how to find it. The Higgs may not stick around for long enough, but its decay products can. Long enough for us to at least detect them. The Higgs could hypothetically decay into almost anything, provided it has a lower mass than it. But the higher the mass of the decay product, the more likely it is it will happen. This graph here shows all the important decays for the Higgs boson, and their branching ratios. A branching ratio just means how likely a particular decay is. Now, as you may have noticed, these likelihoods depend on the mass of the Higgs. So does this mean that the Higgs can exist with many different masses? Unfortunately not. The truth is that before discovering it, we had absolutely no idea what the Higgs mass was. For the purposes of the experiments, this meant that depending on what collision energy the scientists used, it would change the decay that they needed to look for. As we'll see later, the Higgs mass turned out to be at that dotted line on the graph. So let's see which decay modes are most useful at that point. Now in general, the more a decay is likely to happen, the better chance we have of seeing it. But it's not quite as simple as that. The problem is that a lot of these particles are really quite common in a particle accelerator. They're made from other collisions that don't involve a Higgs boson at all. So it becomes very hard to distinguish between these particles and the ones that decayed from a Higgs boson. There are 2 decay modes, or channels, that found use in the initial discovery of the Higgs boson. The golden channel. This is where a Higgs boson decays into 2 Z bosons, which then further decay into 4 leptons. It has a decently high likelihood at 2.6%. These leptons are fairly easy to spot and aren't very common collision products, so when we find one, we have a better idea of where it came from. For these reasons, this decay mode was known as the golden channel. The diphoton channel. This is where the Higgs decays into 2 photons. Now photons have a very low likelihood at just 0.2%, but they are handy for a different reason. We can measure their energy very accurately, so they're very useful for determining the mass of the Higgs. Because as we know, energy is equivalent to mass, so the energy of the photons can give us the mass of the Higgs. So, production mode's done, decay mode's done. Now to look at the machines that made this whole thing possible, the particle accelerators. Before we get into all the different experiments that took place, I need to explain how the search worked. As I mentioned before, we had absolutely no idea what the Higgs mass was before we found it. So here's how the process went in short. Step 1. Accelerate the particles to some speed. This speed determines how much energy the collisions have. Step 2. Depending on the particle's speed, these collisions will create other particles. Step 3. These particles will decay over some period of time into different particles, creating jets of particles. Step 4. Look at these jets to see if any jet particles match up with what we'd expect to see from a Higgs decay. Step 5. If something is found, run the experiment over and over again at the same energy to check that this wasn't just a fluke. Step 6. If a new particle is confirmed to be found, check that its properties are consistent with the predicted properties of the Higgs boson. And step 7. If everything lines up, congratulations, you have found the Higgs boson. One last thing to explain before we get into the experiments though. In the regular world, we measure the mass of things in grams and kilograms and pounds and ounces and so on. But in the particle physics world, we measure the mass of things in EV, or electron volts. All of the mass numbers from now on will be in GeV, or giga electron volts. This just means 1 billion electron volts. So if you see 10 GeV, it means 10 billion electron volts. Now I'm sure we've all heard of the Large Hadron Collider at CERN, who we'll talk about more later on, but did you know about its older brother? Also at CERN, the first experiment to test for the Higgs boson was the LEP, or Large Electron Positron Collider. As the name suggests, the LEP collided electrons and positrons together to make new particles. This is very unlike its successors, who preferred to collide protons together. The LEP definitely wasn't built with finding the Higgs boson in mind, but near the end of its project duration, they got some interesting results, so decided to do a more thorough investigation. At first, the LEP had quite a low mass limit, and was only able to test for Higgs masses up to and around 60 GeV. This was known as the LEP-1 era. By 1995, they had confirmed that the Higgs mass was not between 0 and 60 GeV across their 4 detectors. The next era, LEP-2, sought to widen the search by upgrading the LEP to allow it to accelerate particles even faster, so they could look for the Higgs mass at higher levels. The final result of this was testing done all the way up to 115 GeV. While there definitely were some interesting results around 115 GeV, which could suggest a new particle being made, nothing concrete could be found. After LEP-2, the entire LEP was deconstructed to make room for the LHC. Now, although the LEP didn't manage to find the Higgs boson, it did do very important work. Most importantly, it ruled out the Higgs mass being anywhere between 0 and 115 GeV, which helped future experiments in their search. Our next stop is in Illinois in the USA, where the intimidatingly named Tevatron started collecting data relating to finding the Higgs boson in 2001. Tevatron was working on the search at around the same time as the LHC, but it's much less well known than it. In fact, Tevatron's findings were very similar to the LHC regarding the Higgs, but sadly it didn't have the same Cinderella story. Now, Tevatron had a much higher mass limit than the LEP at 180 GeV, but it had a separate issue. If Tevatron tested any masses below 140 GeV, the majority of decays would be into a pair of quarks, a bottom quark and an anti-bottom quark. Unfortunately, these quarks are very common inhabitants of the particle accelerators, as they can be made from a variety of collisions that don't involve a Higgs boson. This meant that the Tevatron couldn't collect these products with enough certainty that they came from a Higgs boson. But it didn't stop them from trying. All in all, the Tevatron had two major findings. Firstly, it found that the Higgs mass was almost definitely not between 147 and 180 GeV. And secondly, it did have some very interesting events between 115 and 140 GeV. Looking at this graph here, the important area is where the black line rises above the yellow section. In this area between 115 and 140 GeV, Tevatron results show more than a 95% confidence level that a new particle is there. So did Tevatron find the Higgs boson? Well, very likely yes, it probably did create and detect the Higgs boson. But unfortunately, the final result was not a high enough confidence level to be considered legitimate in the science world. Despite this, Tevatron did provide vital information about where the next experiment should look. And that next experiment you might know quite well. The Large Hadron Collider, or LHC, at CERN. Unlike Tevatron, the LHC was specifically built for finding the Higgs boson. This gave it a few advantages over its predecessors. Firstly, it could reach much higher Higgs masses, and so if the Higgs mass was higher than 180 GeV, the LHC would be able to find it. Secondly, and more importantly, the LHC was able to distinguish the significant events from the background much better than Tevatron. Remember that Tevatron had a lot of events between 115 and 140 GeV, but they were unable to get the results to a high enough confidence level. If the LHC detected these same events, it should be able to distinguish them much more precisely. One other advantage the LHC had was that there were two separate teams looking for the Higgs, Atlas and CMS. These two teams were not allowed any contact with each other. This meant that there was no bias in the data if something was found. By having two teams looking for the same thing, you know with much more certainty that a result is legitimate if both of them find it independently. The LHC started by checking over the regions that Tevatron checked, and a little beyond. Atlas excluded 155 to 190 GeV, and CMS excluded 149 to 206 GeV, both with a very high confidence level. By December 2011, they had narrowed down the hopeful range to 115 to 130 GeV. They hoped that the Higgs boson was somewhere in there. It was only a matter of time. This God particle would be found.
This is a very, very preliminary result, but we think it's very strong. It's very solid. Otherwise, we wouldn't present it. And we've slowly, as we've gathered data, rediscovered the standard model to more and more rare processes, and basically we're very confident now that we can go after the rarest, which is the Higgs. If we combine the ZZ and gamma-gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, They combine to give us a combined significance of 5 standard deviations.
Should I say that I'm pleased?
Congratulations.
I think it's obvious.
This is still mine, right?
This is still yours, yes.
As a layman, I would now say, I think we have it. You agree? Yeah.
Let's quickly cover what they said. They said that CMS had discovered a new particle at 125.3 GeV, and Atlas had made a similar discovery at 126.5 GeV. By combining these two results together, they have a significance of 5 sigma. What is 5 sigma? Well, it basically means that there's a 1 in 3.5 million chance that the results they got were just due to pure luck. 5 sigma is generally considered the gold standard in physics. It was a pretty chilled out announcement for one of the biggest scientific discoveries of all time. But there was reason for this. The scientists didn't actually know what they had discovered, just that they had discovered a new particle. It could have been something entirely different to the Higgs boson, something not in any of the mainstream theories that anyone had. So the scientists got back to the grindstone. And finally, on the 14th of March 2013, almost 50 years after the original theorization of the Higgs, the CERN teams released this statement. CMS and Atlas have compared a number of options for the spin parity of this particle, and all these prefer no spin and even parity. This, coupled with the measured interactions of the new particle with other particles, strongly indicates that it is a Higgs boson. In short, the properties that they detected for their new particle matched those that the theoretical Higgs would have. As always, this wasn't the end of the story for the Higgs, or the field of particle physics in general. The Higgs still needed to be tested in a variety of ways to ensure that it behaved as theorized. The metaphorical book of particle physics is still being written to this day, with new chapters being started all over the world. But at this moment, we can close one of the greatest chapters of all time. The day science found God.
Ladies and gentlemen, it is a great honour for François Englert and me to receive the Nobel Prize in Physics, and we wish to express our sincere gratitude to the Royal Swedish Academy of Sciences and the Nobel Foundation. It is a matter of great regret for both of us that Robert Brout did not live to share the prize with us. The fact that it has been awarded to just the two of us implicitly recognises his contribution, as is right. However, it should be remembered that the three of us were not the only theorists who contributed to the elucidation of what is now called the BEH mechanism about 50 years ago. The long time gap between the theoretical work and the award of the prize is largely a consequence of the difficulty of performing the experiments needed to detect the new particle that is an essential feature of our theory. More than 30 years of work on the development of accelerators, detectors, and computer programs have culminated in the discovery claim made by CERN in July 2012. It was a great achievement by all the people involved and we are grateful to them for enabling us to be here today.